Anyone have an answer? Yeah, you got it. Okay, Michelle. What is your, I'm assuming this is, you drew something like this. Carbon in the middle, fluorines, and it doesn't matter where you put the fluorines and chlorines, because each one of these is going to be 109.5 degrees from each other, and they're all constantly revolving around fluorine atoms, so they could be in either place at one time. So you could have drawn it like that, or you could have switched it up. You could have put the fluorines across from each other. It's all the same thing. Okay. Out of curiosity, what is the molecular geometry of a carbon with 4 bonds to it, or anything with 4 bonds to it like this? Tetrahedral. Tetrahedral, right? What is the electronic geometry? I'm going to start abbreviating molecular geometry, big M, big G, and then electronic geometry, big E, little g, or big G. Okay. So we said molecular geometry is tetrahedral. And electronic geometry, if there's no lone pairs, then the molecular geometry is the same as the electronic geometry. So in this case, it would be tetrahedral as well. Electronic geometry is basically the geometry of the electrons. Where are they oriented in space? Now, when you get into molecular, did I say electron? Yeah, electronic is the orientation of the electrons, but molecular is actually how these atoms are oriented. So if we look at something like this one that we did earlier, what would be the electronic geometry of this one? How many bonds or how many electron domain or electron regions are there around nitrogen? 4, and that corresponds to a electronic geometry of all these on the left are electronic geometries. So if you have 4, it's automatically tetrahedral. That's the electronic geometry. Okay. But once you start adding lone pairs, you start changing up your molecular geometry. Now just like the one that we just saw, the NCl3, its molecular geometry is trigonal pyramidal, right? But it's electron. Am I saying this right? So the molecular geometry is trigonal pyramidal, but its electronic geometry is still tetrahedral, just because it has to do with the orientation of where the electrons are. It's a little tricky.
So in case that made absolutely no sense, electron geometry is where, like, it's how the electrons are oriented around the atom, and then molecular geometry is like what shape the molecule actually takes. Like if you were to like zoom in on like the molecular structure of it, like NCl3, it would look like a pyramid almost. Like lone pair would be on top, and then the 3 chlorine atoms would be to the side.
Like that. But again, it still has that electronic geometry of tetrahedral. It's roughly the same. Okay, let's try another one. I'll give you all a second to do G. Let's jump down to G, PI3. How many valence electrons do we have here? 26, right? So 26 valence electrons. We know phosphorus is going to be our central atom. And if you recognize that, you start noticing a pattern. So phosphorus and nitrogen are in the same group. Iodine and chlorine are in the same group. Therefore, these should bond the same exact way, and they do. So what we see is that you would have 3 lone pairs around iodine, each one. And then that 1 lone pair on bottom. So once you start doing a lot of these problems, you start recognizing patterns like, oh, PI3 is going to have a similar geometry and electronic and molecular geometry as NH3 or NCl3, you know. Not NH3, because there's no bond, but NCl3. And if you do that, again, you would figure out how many bonds, so I'll raise the. What we want to do is you say you have 26 valence electrons, right? Always start by a single bond to each terminal atom. So each iodine should have a single bond to phosphorus. In total, we used up how many electrons so far?
6.
Right, we got 2 here, 2 here, 2 here, 6. So -6, that's equal to, we have 20 left over that we still need to use. So each iodine needs a total of 8. Right now, they're sharing 2, so they have 2 right now. So we need 6 here, 6 here, and here as well. So that's 6, 12, 18. Phosphorus doesn't have a full octet, so we're gonna add 2 here, right? Because right now it has 6. It has 2, 4, 6. So phosphorus still needs 2. So we need 6 on each iodine. That's 18 plus the 2 here, so that's gonna be 20. So we put all of our lone pairs in. That's gonna be -20, and you get 0 left over. Okay. We're gonna jump back up to E. Right? I'm just trying to use things because a lot of space here. Okay, go ahead and take a second on this. E. Have them with your meeting. Have them with your meeting.
Your name. Like that.
Formaldehyde. Oh, well, that's a common. At the now. At the anal.
It's got a call.
So I keep them.
Yeah.
All right, so what is going to be our central atom? How do we know that? Yeah, and typically whenever you see carbon is always going to be your central atom.
Are there exceptions?
What?
Exceptions?
So where carbon's like not the central
Yes.
atom? Not that I've seen.
Like if carbon's in a molecule, it's typically always going to be a central atom. Right? Which is why it's so complex. They have a whole 2 classes dedicated to just that. Y'all will learn a little bit about that. So carbon is our central atom. And like I said, we always want to draw a bond to each terminal atom, right? So we have an H, and then an O. Before we go any further, we need to figure out how many valence electrons we have. How many valence electrons in total do we have? We know carbon has 4, oxygen has 6. Each of these brings 1 to the table, right? So we have 12. Yeah. All right. So we get rid of those numbers. We used up how many in the bonds? We used a total of 6, right? So now we have 6 left over. -6 electrons equals 6, right? How much do we need? How many more electrons does hydrogen need? None, right? Because hydrogen can only hold 2 electrons in its outermost shell. So we don't need any more here. What about carbon? H2, right? Because it needs to fulfill the octet rule. Right now it has 6, it is deficient 2 electrons. So we need 2 here. What about oxygen? 6, right? Because it needs to fulfill the octet rule. Right now it only has 2, we need 6 more. So we need 6 on here, 2 on here. So that's a total of 8 that we need. So, oh, look, we're taking more than what we have. We end up with a -2. That tells us we need to add a double bond somewhere. So where would we want to add the double bond besides? Go ahead. Yeah.
On the other.
On the, between the C and the O, right? Exactly. Why not anywhere, why not between the C and the H?
The H can't hold more than two.
Exactly, right? So the H, we wouldn't want to put it between the carbon and hydrogens because the H hydrogens can't occupy, they can't hold more than 2 electrons, right? So the only place that you can put it is between the carbon and the oxygen. So now all this, we'll redo it just to make sure. So right now we have 2, 4, 6, 8 electrons being used. 8 electrons, so that gives us 4 left over. Carbon, how many more does carbon need? Are you sure? Look at, so remember each bond, yeah, it needs 0, right? It already has a full octet because it has 1 bond, 2 bond, 3 bonds, 4 bonds. We know carbon likes to form 4 bonds. If it forms 4 bonds, that means it's sharing 8 electrons, right? So it has a full octet. Oxygen has total of 2, 4 right now, so it needs 4 more, right? And look at that, we have a perfect amount left, minus 4 electrons. This gives us 0. So 1, 2, 3, 4. What is the molecular and electronic geometry of this right here? So, yeah, trigonal for what? Or for both, yes. Yeah, so it's trigonal planar, right? You can't just say trigonal because you got a lot of trigonals up here. You have trigonal planar, you got trigonal pyramidal, trigonal bipyramidal. All these things that you have to memorize for your test. All of these. Each one. Okay. So yes, what would the bond angle be in a trigonal planar geometry? What? Oh, 90. 120. 120 makes sense, right? Because we know electrons repel each other. So the way I drew it is completely wrong. What you would actually see, what it actually looks like. Let me erase that too. Is you have a double bond here, that there, and that there. And each of these would be approximately 120 degrees. And there, 120 degrees. And there, 120 degrees. Because that's, since they're all on the same plane, that'll allow the electrons to be spaced out as far apart as possible. We know they don't like to be next to each other, right? That's the Vesper theory. Yeah.
So like would Dr. Armour will test us on this to like make sure we drew it correctly like that.
Not if you drew, it's gonna be multiple choice test. Okay. So you don't have to draw it correctly, you just need to know the bond angles. And if you were to draw it the way we had drawn it before, like this,
You would just have to know that's 120.
yeah, you would have to know it's 120, and you can't say, well, that's gotta be 180. And this has to be 90, because that's wrong, right?
Please don't pull out a protractor and measure those angles. They're not gonna be right. Just memorize the bond angles.
That's-
Can you explain the difference between like molecular geometry and electron geometry?
Yeah, so electron geometry is the arrangement of the electrons around the central atom. The molecular geometry is the actual shape that the molecule takes. So the best example is probably going to be doing something like ammonia. Okay, NH3. The atoms are arranged in a the electrons are arranged in a tetrahedral electronic geometry. So if you could kind of think, you have an electron cloud like that, like that, like that, and like that. That's the trigonal or tetrahedral formation, right? But however, because you have a lone pair here, what the actual molecule looks like is that it's this lone pair is pushing down on these bonds. So it's actually making it look more like a pyramid. So you would have something like your H here. This would be coming out towards you. And this would be going away from you. You got a little pyramid shape there, and then the lone pair up there. So when we don't have, what is it?
When we don't have pairs of lone electrons, electron geometry is the same as a molecular geometry.
Exactly, yeah, so when we don't have pairs of, or lone pairs, I see up here, electron geometry is equal to, or the same as your molecular geometry.
That's
Or not,
because,
yeah,
yeah, it's because lone pairs mess with the bonding. So like, if you have, say, more lone pairs, it actually make the bond angle even less than what it should be.
Yeah, so that previous example we did, we had this here. The lone pairs on the molecular geometry and electron geometry are both trigonal planar, right? But if we take something like water, or I don't know what it looks like this. Actually, let's just do water. Water would have
It looks like what?
that one right there, the bent or angular with one lone pair. Okay, so water has total of 2 lone pairs on the oxygen, right? Because it has 4 electron-rich regions, the electronic geometry is considered tetrahedral, all right? You just have to count your electron groups. So one here is in the bond. You got another lone pair, which is occupying its own electron area. Another one here, another one here. So we have a total of 4 electron groups. That corresponds to an electronic geometry of tetrahedral, okay? But because these lone pairs actually affect the bond angles, water has a bent shape, and that is the molecular geometry. So you would see, if it asked you, what is the molecular geometry of water? You would say it's bent. If it asked you, what is the electronic geometry of water? You would say it's tetrahedral, okay? And all has to do with the arrangement of the electrons versus the arrangement of the atoms, okay? So, any questions so far? How are we feeling about this so far? Not good? Good. Okay. I'm just kidding. Let's do F. Let's go ahead and do F. How do you know when to put a double and single bond? We'll go over that in just a second, Alex. F, yeah. Let me erase these. Let's do, yeah, go ahead and work on the highlighted one. Where did you find it?
I got it file on.
It's a gift.
Looks like a steroid.
Oh, I'm telling him you said that. I want it. I want it.
You know what steroids are? What they're classified in terms of bio? They're lipids. What's the most abundant steroid in the human body?
Probably estrogen.
It's cholesterol.
I'm a skin so not for me.
Yes. All right, so let's go ahead and do this. What's our central atom? Carbon. We all agree on it's carbon, right? Because carbon loves to share its electrons. So it's so giving, all right? So let's put carbon in the middle. Now we always draw a single bond to each terminal atom, right? So N and then H. We always draw a single bond, right? Now we can count how many valence electrons we have. How many valence electrons do we have total with the CH in the end? 10, okay. We're trusting that Maria passed Cal for biosciences and she can count.
I actually have a 103 in it right now.
Perfect. Okay. So 10 electrons, valence electrons. We used how many in the bonding so far? 4, right? We used 2 here, 2 here, that's 4. So minus 4. We have 6 electrons to spare. How many more do we need on nitrogen? We need 3 electrons.
Three pairs.
So how many electrons? Okay, so we need 6 on nitrogen, right? I'm gonna put them in red. We need 6 here, and we still need how many on carbon? 4, right? So 6 plus 4 is 10. If we try to take 10 away, we end up with -4. That doesn't make sense, right? And then every time you end up with a negative number, it means that you need to add either a double bond or a triple bond. And since -4, we're deficient a total of, if you divide by 2, this tells us you're deficient like 2 bonds, right? Because each bond carries exactly 2 electrons. So right now we need to add a double bond, either you can add 2 double bonds or a triple bond. What do we want to add, 2 double bonds? Or do we want to add a triple bond? Triple bond, right? So I'm gonna erase these red electrons. I'm gonna erase this stuff here. So we add a triple bond right here. So now we have 10 we already start with 10 valence electrons. How many have we used up in bonding so far? 8, yes. So now we have 2 electrons left over. Does carbon need any more?
No.
Nitrogen needs 2, right? Because right now it only has 6. It's deficient in its octet. So we're gonna put the 2 there. We're gonna subtract that 2. And we end up perfectly at 0. And everything is filled by the octet rule, right? Nitrogen has 8, carbon has 8, and hydrogen has 2. Okay. Any question? Yeah. Yeah, so it's linear and like you said, it's for both the electronic geometry and the molecular geometry. The lone pair is not on the central atom.
Oh,
Remember, we only look at the central atom when we're talking about lone pairs, because up here you have lone pairs all over your chlorines, but they don't affect, that doesn't affect the overall molecular geometry, only what's on the central atom. Okay. All right. How about we do? You have a good one for them, Rich? In your head, maybe?
So it doesn't have to be on here.
It doesn't have to be on here.
All right. XEF2.
XEF.
No, make that as false. XEF2.
All right, xenon tetrafluoride. Believe it or not, xenon does make bonds to other.
This is an exception.
It is an exception.
Could be, could be.
You want to do this one?
Oh, yeah.
Can you explain it real well?
That's wrong. I think next week.
What is? That how you draw lone pairs?
No, it's not. It could or it could not. Draw your dots, maybe. It'll correct.
I don't mind.
Oh my.
It's not a bond, it's lone pairs.
That looks fine to me. That looks easier. To do this.
If I grade your take home assignment and I see lines, I'm taking 20 points off.
Yeah, he takes random.
I have like double bonding.
Oh wait, I'm the one reading your take home assignment, so I'll probably take off one.
Who has an answer? Who is also confused? And also assign the electronic and molecular geometry.
Dude, I never learned that. I regret it now. You know what I don't understand? Why it's not.
Because it's the one.
And then you can show them the trick of how to do it.
I was blind.
Well, do it the long way and then do it this way. And you always gotta show them, drag them through the trenches before you pull them out.
You know what, Dr.
Yeah.
Mom was your kid? Made you get up there and brought it from the whole and I died. I was dying on the inside, and you made me do another.
And if you were to have a metal and not
I
your
cried.
I don't want to know that.
Yeah,
You think so.
like you had.
Like sodium, lithium. So that was. You can't draw.
So your very strong structure stuff only applies.
Covalent.
Covalent.
Yeah,
Okay.
so like.
Oh,
Sodium chloride.
oh, hi, hi. It's here, there. Oh, Rich, just come up. Okay. I know I do.
You could. No, I have 8 now. What's I have 8 now because.
What
transfer-
do you-
Transfer what? Oh, you have to demonstrate.
And that's demonstrated by the plus chart here. the minus chart. Some people have drawn technically arrows with those dotted lines, but
Dylan, for the last one that we did,
They're not actually-
He's just being picky with this whole like. Like loose dot structure.
Should only apply to like covalent. bond.
Yeah,
No, that's a good point. You shouldn't, yeah, drop the structure for an ionic.
Unless it's not a-
Oh, yeah.
No.
Wait, I had a question about the exceptions for.
Aguilar.
for
I got
electronic
one.
voting. So does it go down?
Okay, I signed up for spots next semester.
Like the.
But not tungsten.
Uriel again.
Really?
Yeah. For scars, yeah.
You can.
It said all the way down.
Yes, I'm so happy. I was so sad. I was like.
But also.
I've always known it was chrome, silver or
All right,
copper.
raise your hand if you all have answers. I will try.
We'll just cross our fingers that this show. The tungsten specifically.
All right, 2 more seconds.
But all the tests are the exact same. throughout the class, or all of them. I don't remember seeing. I can.
You believe or do you know, Michelle? They have an answer.
Yes, you
Is one of the city codes. Your electronic configurations or-
I'll send out the next one, Michelle. It has its own exception.
Yeah, so I just compared and said that it doesn't.
Yes.
He agreed that it doesn't.
Are you 100% confident that? Can you say with chest that it has 2 lone pairs?
I think it has 2 lone pairs.
It's
It's like, and it's kind of bent because of that. So maybe the electron geometry is like a square plane.
Interesting. Interesting indeed.
Right there.
All right, I'm gonna go ahead and go over it. So how many valence electrons do we have total in this? 36. 36, let's see. So fluorine has 7, right? And then xenon has 8. So that times 4 is 28 plus 8 is 36 valence electrons. And then, right, what's your central atom?
You know,
Why?
because the halides are not central atoms,
Why not?
because they can only form one bond, single bonds.
That is true, but what I was going for, right, xenon's actually the least electronegative out of all these atoms. The least electronegative atom is always usually a central atom. So you're gonna put xenon in the middle, and then you're gonna surround it by more chlorines. What's our next step?
Put a
Yeah.
bond between each of them.
Yeah, put a bond to each, so here's one, here's another, here's another, here's another. How many electrons did I use up? 8, yeah, so 36 minus 8, that's, we can do math, 28 valence electrons. I can do. So we have 28 valence electrons left, right? How many electrons does fluorine need to satisfy his octet?
24 for all of them. So it's
24.
6 each.
6 each? So you're saying something like this, where you put lone pairs around each. It is dots, by the way, not lines. One big thing. How's it take? I'm already done. So how many electrons did we use during all this ordeal? 24. So we have 4 electrons left. But wait, everything's satisfied. Xenon has 8 electrons, fluorine has 8 electrons. What do we do?
Just forget about the 4 electrons, right?
Xenon can take more
Why can it take more?
because it's past row 3.
It is indeed past row 3. It's got that D subshell, so it can take more electrons. It can take more because it has the D subshell. So you can put 1 lone pair right here and then another lone pair right here. That's 4 electrons, right? So yeah, 4 minus 4, 0.
Boom.
How many of y'all got that?
So what did y'all get for the electronic geometry and the molecular geometry and I know you were looking at your notes. Anyone else?
The electron geometry is square. I don't know.
So electron geometry, so you remember your electron geometry can only be linear.
How can you?
Trigonal, planar, tetrahedral, trigonal, what is it, bipyramidal?
Wait for
Is it
electron.
octahedral?
It is
It is
indeed octahedral. As your electron geometry, octahedral. Why? Because there's 6 different groups surrounding the xenon. So one here, one here, one here, one here, maybe 2 lone pairs. So in total, that's 6. So 6 groups around it, you know that's octahedral. And then what's your molecular geometry?
Yes.
Square planar?
Oh, that's the molecular square.
Yeah.
So it. I thought it was, oh wait, never mind, sorry.
Someone said in the chat, does the placement of the electrons around the central atom matter?
Not really, but it looks prettier if you space them out.
Yeah. It does look prettier.
Yeah.
So to answer your question, no, it doesn't matter, but typically electrons like to push each other far away, right? So you put them on opposite sides.
Any other questions?
And then what is the molecular geometry?
So six.
Square planar, yeah.
It is indeed square planar. SQUARE.
Yeah, you're right.
Let's go up here to see what that looks like. So octahedral electronic geometry. Looks something like that one on the left, whereas square planar, it literally looks like a square. Yeah.
Like legit, like for xenon, right? Your fluorine atoms will make like a 90-degree angle with the xenon, so it'll be like something like that. This, and then the same thing at the other side. So that one, I think here, split some money. And or here, notice how this is, it looks like a 90-degree angle, so it does make 90 degrees, and then you have these 2 lone pairs up here in the plane. So like these lone pairs will be flat, and then you'll have one, like 2 of the fluorines will be like coming out at you, and then like 2 of the fluorines will be going in.
Want to show me your faster way to do it?
Yeah, and how many of you were taking a long time on this problem, struggling, some might say? Do you guys want to know a trick so that you can get through this faster?
Do by pairs. I just do by pairs.
Yes, please.
Divided by 2.
Yeah, that's actually the trick I was gonna show. So
Yeah.
Dr. Armand actually taught me this trick back in the day when I took Deck M1. So let's erase this and then do it again. Okay, so let's do it again. Xenon central chloride. Now, again, how many total valence electrons do we have?
36.
36, yeah. So how many terminal atoms do we have? Like atoms around the central atom. 4, yeah. So what you're gonna do is you're gonna take those terminal atoms, and each of those terminal atoms needs 8 electrons, right, to be satisfied. So what you're gonna do is multiply that by 8. So 4 times 8. What's 4 times 8? 32, exactly. So then you have 32 electrons right here. Now what you're gonna do is you're gonna subtract this 32 from your total valence electrons you have. So 36 minus 32. In this case, that's equal to 4. What that means, right, is that since all of our terminal atoms need 8 electrons to be satisfied, there's an extra 4 electrons we have somewhere in the molecule. And those 4 electrons, right, have to go on your central atom. So if they have to go on your central atom, we don't typically represent electrons as like, not for this class, we don't typically represent electrons as like one thing, like if it's like just one electron like that. We usually represent them as lone pairs. So what you're gonna do, right, is you're gonna divide those electrons by 2, the 4 electrons by 2 to get the amount of lone pairs you have. So 4, right, divided by 2, you'll get 2 lone pairs on the central atom. This is a shortcut way for anything to find the lone pairs on the central atom. So take, for example, right, let's do another one real quick, NH3. You know that there should be 1 lone pair right on the nitrogen, because we did this problem before. Let's confirm that real quick. Or wait, it might not work. 4, 7, yeah. Let's try something else. Let's try the other one, PI3. This one will work. So how many valence electrons are in PI3 total? 26, yeah. And then what's 3 times 8? 'Cause that's the amount of terminal atoms. 24, yeah. So 26 minus 24 is 2. You divide that by 2, that's 1 lone pair. And as you saw in this problem, phosphorus did indeed have 1 lone pair. So that's kind of a shortcut way to do it. The reason why this is a shortcut is look at this. Xenon, right? You already know it has 2 lone pairs, so we can slap those on from the beginning. And then we can do our similar process. So 1 fluorine here, 1 fluorine here, another one here, another one here. And then we have 24 electrons left, right, total. So now we can just put those as lone pairs on us. There we go. You have that structure drawn in about 2 minutes.
All right, got some time for a little bit more. Do a hard one. Let's do water. How about we do ozone?
Oh, 3, yeah.
Yeah, O3, yeah. Yes.
But that one Drake's on. So that O2 to that O3.
Right, Audie, you have an answer? All right. Oh, it's wrong then.
I think you're trying to-
After this, we should do XeCl2.
I did. This is chemistry.
All right. Go ahead.
All right.
What's our central atom here?
Oxygen.
Are you sure? Yeah. I'm just guessing, yeah.
Yeah, it's oxygen because it's the only atom we have. So oxygen right here, right? Now we're gonna put 2 more oxygen around. So what's our next step now?
Connect them, bond them.
First of all, let's calculate our valence electrons. How many valence electrons do we have?
18.
18, exactly. So 18 valence electrons. Now we're gonna do the step of bonding. So 1 bond here, 1 bond there. So 18 minus 4, you have what? 14 electrons left, right? How many electrons does the oxygen on the left need to be satisfied? Yeah, so let's go ahead and draw those lone pairs. 1, 2, 3, 4, 5, 6. Now, how about the one on the left? 6 as well. So 1, 2, 3, 4, 5, 6. How about the oxygen in the center? 4, yeah, so 1, 2, 3, 4. So how many is that? 6 plus 4, 10, 10 plus 6, 16. So 14 minus 16. Oh no, we have -2 electrons. Whatever shall we do? To which oxygen? Yeah, it is indeed you can draw a resonance structure. So where, like, if you were to look at this molecule, right? Where would the double bond be? On the left oxygen or the right oxygen? The answer is it flips between both of them. So like sometimes it could be on the left oxygen, on other times it could be on the right oxygen. It doesn't matter which.
So this is something called resonance structure.
Yeah, this is resonance.
And it has to do with the idea that electrons don't just occupy one spot at a single time. And that they can occupy, they're constantly moving, and if there's an area that an electron can move to, they will. It's just, I guess that's the basis of resonance. So like, Rich, you want to show them like the curved arrows of where the electrons could be moving?
Yeah, so let me draw both resonance structures first.
Yeah.
So one resonance structure will look like this. Then another one could look
Yeah.
like this, where you have oxygen right here. 1, 2, 3, 4. Yeah, that is. Yeah, that's right. Another resonance structure could be like this. Where the double bond is on the left side now instead of right. Like that.
Are you getting your left, right?
Well, this is the right, that's the left. Right side, left side.
Yeah, okay.
There we go. Okay, so, well, what do I mean by this? So the oxygen, the double bond could either be on the left oxygen or the right oxygen. And as a matter of fact, it flips between them. So what happens, right? This is something called a resonance hybrid. So this is what the structure will look like in real life. It'll be a combination of these two. So what'll happen, right, is you'll have your oxygen right here. These bonds, right, will stay the same. But then you have a double bond sometimes over here, or you could have a double bond sometimes over here. That's what that dotted line is for. It's to show that like sometimes a double bond could be on the left, other times it could be on the right. It always like flips between the two. And then right, you got learned about formal charge yet? Okay, so we'll leave it at that. Technically, you'd also have to put your formal charges on here, like this oxygen would be positive, and then this, one of these would be negative. In fact, both of them would be negative at one point. But yeah, that's basically what resonance is. It's the electrons split between atoms.
Oh.
Because, yeah, that's to do with the formal charge.
And those lines.
Yeah, it's a delta. It's like this slightly positive.
Oh, is that like the partial positive?
Yeah, particle positive, particle. Yeah.
So both,
So
Yeah,
in the
so-
one that's not a resonance structure, would that be like 1 plus and then 2 minus and then 0?
Which one are you talking about? This one?
If you had like that one with the double bond on the left side, would that
On the
be,
left side, yeah.
would that have 2 minus and then 1 plus and then 0? Or
It'd actually be like this. If you're talking about formal charge, it'll be 0 on this one, +1 on this one, and then -1 on this one. And then the reason, right, why O3 is neutral, it has no charge, is because it has a 0 formal charge. Like if you had like +1 and -1, right, they cancel to be 0. So yeah, that was just a bit of intro to resonance. And to answer your question, Michelle, it does, like, both would be considered correct. So like, if you draw it on the left, it doesn't matter. If you draw it on the right, it also doesn't matter.
I have a question. So the reason the oxygens on the outside are partially negative is because they're pulling the electrons?
So the reason why they're partially negative has to do with their formal charge. So in this case, right, the oxygen owns more electrons than it needs.
Yeah.
That's why,
pulling-
yeah.
so this one right here, it has a single bond to it, right? Where, and it has 3 lone pairs. Oxygen typically has how many valence electrons? 6. All right, so it typically has 6. So it typically has 6, right? And this is equal formal charge.
Linear.
So you go based on how many electrons it normally has
Minus the amount it owns.
minus the amount it owns. So in this case, oxygen has these two, these two, and it's contributing 1 to this bond, right? Because there's 2 in this bond.
Oh, yeah.
So it's contributing 1. So we have a total of 2, 4, 6, 7, right? Because this bond has 2 electrons. So that's 6 minus 7, which gives us a -1 formal charge, which is why it has a -1 partial charge on it. And again, it's because typically oxygen is found with 6 valence electrons. In this case, it technically has 7 valence electrons,
Oh, I see.
which is why we see this.
Are we gonna get into this?
This will be later in the chapter.
Any questions on that? Let's do one more.
A request for XCCl2. Or F2.
CL2. All right, you got 15 seconds. After his little trick, it should take no more than 5 seconds.
Which is. Embarrassing.
done by number, yeah.
I'm straight.
This is 8.
All right, time's up. I'm just kidding, just kidding. We got until 6 o'clock before the grad students start coming on and come and bang on the doors.
Or just come in.
All right, now time's up. Okay. How many valence electrons do we have here? 22, because we have 7 here on each fluorine times 2, right? So that's 14 plus 8, 22 valence electrons. How many terminal atoms do we have? So we have 2 terminal atoms, but terminal atoms, and each one needs how many electrons? So 16, right? So now we have to do 22 minus 16 electrons is going to be what, 6. So there's 6 electrons left over. We know that these electrons come in pairs, right? So we do 2, that's 3 lone pairs. That's 3 lone pairs that are going to go onto what? Do we all agree that it's going to go into the central atom? Yes.
Why wouldn't it go on the fluorine?
Fluorines already have their oxygens.
Like fluorine emits.
Yeah.
If you've got an atom past row 3 bonded to atoms past row 3, could you have multiple atoms with more than an octet?
Generally, right, if you have something like that, only your central atom will break the octet. And then your surrounding atoms. Like if you take our example, right, like Pi3, like phosphorus is on row 3 and then like iodine's on row 3. But like, or in that case, phosphorus didn't break the octet rule, but say for example, you have like larger atom like xenon or something. Xenon's the only one that would break the octet rule, but then all the other ones have a be stable.
I forgot to draw my phone page.
The reason for that is because like the formal charge would be kind of whack if you like if you start messing with like the lone pairs on the octet.
Or it'd be like more than 1 and -1.
Yeah, your formal charge would be neutral.
Yeah, so thank you. Michelle was on top of it. Okay, so how many electron rich regions are around xenon? 3? 5, right? We got 3 lone pairs, that's 3, and the 2 bonds, that's a total of 5, right? So if you were to memorize your little chart up here, the one that has 3 or 5 things around it is going to be trigonal bipyramidal. Okay. And where was it? So electronic geometry is trigonal. That's so bad. And then if you take Dr. Armand, he'll say bipyramidal.
That is not.
And the molecular geometry would be what? Linear, right? And that's it, folks. We are done for the day. Yeah. What? You want to see the chart, Audie?
Because the 2 things over here, the 2 atoms like.
Sorry, I'm just.
Have a good day, guys.
Sorry.
Why didn't you bring some of the Armand?
Notability.
I know that would be a good one.
I could. I have one. I've never. I have it in the package.
That's okay. Little big ball thing.